Problem 20, which of the following transition matrices is not regular? Okay? Not regular. I find people don't know what this means. Regular, that definition is when some power of the matrix contains all positives. Okay? It has nothing to do with the fact that these numbers add up to 1. I don't care about that. Okay? Yes, that's going to happen, but that's just that's not the definition of regular. I'm looking for some power that contains all positives. And so let's look at A. All right? Matrix A right here. I'm going to take that over to matrixcalc.org. And matrix A was 0.5, 0.5. It was 010, 001. And it looked like that. Okay, I'm just going to double check, make sure. Yes. Okay, so some power of that has to contain all positive entries. In other words, get rid of the zeros. I'm going to square it. I still see zeros. I'm going to cube it. I still see zeros. To the 4th, zeros. To the 5th, zeros. To the 6th. I'm just getting a strong feeling that it's always going to be zeros. I'm going to try the 99th power. It sure looks like it's always going to have zeros. Okay, that's not a rigorous proof, but that's good enough for me to know that this one is not going to be regular. So let's try the next one, 0.75, 0.25. Okay, 5.5 and 6.4. So clear. It's 0.75, 0.25, 0, 0.5, 0.5, and what was it? 5.5 and 6.4. I believe it was that. Okay, so I'm going to just look for some power to have all positives. Ooh, I squared it, and there we go. All positives right there. So that's what it takes. That's what's going to be, that one's going to be regular. Oh, and guess what? This one already has all positives. Don't even have to do anything to that one. I don't have to take it to the second power. For this one, I squared it, but this one's just positive already. So both of those two, B and C. 21, determine the long-range probability that someone who starts in state 1 will end up in state 2 for the absorbing Markov chain. Okay, absorbing Markov chain. So we've already done long-range probability, but absorbing Markov chain is talking about these absorbing states right here. Well, for ones, that means if you start in state 2, you're going to be stuck in state 2. If you start in state 3, you're going to be stuck in state 3. But let's look at the long-range probability and see what that means. 325. Long-range probability. We'll take it out to some high power. 99 usually works well, so I'll do the 99th power. And I get something that looks like this. It'd be nice if I changed those to fractions. I don't really care about that all that much. I believe that's 2/7 maybe. But anyway, I don't totally care about the fraction for right now. So let's look at that and let's talk about that for a second. Okay. So what I did was I took this to the 99th power, and I got this. I wanted some long-range probability, and so it's different. Sometimes when we do long-range probability, the 3 rows match. And the 3 rows don't match here, but that's because the absorbing states do something weird, all right? And where you end up depends on where you started, okay? So you have to think about where you started and where you ended. So the right answer has to do with where you started and where you ended. Basically, determine the long-range probability that someone who starts in state 1 will end up in state 2. Well, I'm going from state 1 and ending up in state 2, so the answer to that question is just the 0.28. You can convert that fraction if you like.